Our next speaker is Marek Petrik. He'll tell us about tight Bayesian ambiguity sets for robust MDPs.
All right, thank you. So this talk is about robustness in reinforcement learning. So why do we actually need to worry about robustness in the first place? So we are interested in the batch reinforcement learning case when we're learning from log data. And since this is all the data we're ever going to get, the data is often limited, which causes our transition probabilities to be uncertain. Now, when we use these possibly incorrect transition probabilities to compute policies, we often get policies that are really brittle and fail easily when deployed. This may be okay in some domains, but in medicine, industry, and other high-stakes applications, this is not okay. It's not okay to do a trial and error approach. So the goal of our work is to compute policies that are robust, but we want to do it in a way that we don't end up being too conservative. And our general approach is to use robust MDPs and to optimize the size and the location of ambiguity sets using Bayesian models. So our setting is the standard batch reinforcement learning setting. We're assuming we are given a batch of domain samples, logged data. We don't have a simulator, so this is simply a sequence of state action pairs and their rewards. And we want to compute a robust policy. What I mean by a robust policy is a policy for which we can guarantee a lower bound on the true return when the policy is deployed. So this doesn't mean that we always can compute a good policy, but this means that we can detect that our policy is bad before we actually deploy it. We can tell from the data alone. The approach to computing this robust policy is simple. We use our data to estimate a return on the policy, and we want to do it in such a way that our estimate is a lower bound, so it's a pessimistic estimate of the true return. And at the same time, we want to make sure that the estimate is tractable, that we can compute a policy which will maximize the estimate on the return. So we can simply solve the maximization problem. So how do we construct such an estimate? One convenient way is to use robust MDPs. So robust MDPs are very similar to regular Markov decision processes, except instead of a single transition probability, we assume we are given a set of plausible transition probabilities, and then we look for a solution that's good with respect to the worst case realization of a transition probability within this plausible set. The plausible set is usually called an ambiguity set. So on the bottom of the left-hand side, you see the projected simplex of a transition probability from a single state and action in a regular MDP. And on the right-hand side, you can see the ambiguity set for a robust MDP. And I just mentioned that robustness is generally very similar to doing regularization in machine learning. So the challenge we're addressing in this work is how can we actually construct these ambiguity sets in a data-driven way? You can intuitively see that if your ambiguity set is too small, your solution is not going to be not going to be robust. But if the set is too large, your solution is going to be very conservative and practically useless. So the standard approach to this problem, which has been taken by many algorithms, including UCRL and others, is to use concentration inequalities to construct the ambiguity set around the maximum likelihood estimate. So on the bottom, you see such an ambiguity set for 30% confidence interval and for a 90% confidence interval. Theoretically, this is a nice approach. It's very simple. Unfortunately, it doesn't work in practice and typically leads to solutions that are robust, but very, very conservative and unfortunately practically useless. So our goal in this work is to improve on this. And these are the three main ideas that we're using. So first of all, we want to capture any possible prior information using Bayesian models. Then, instead of simply constructing the set around the maximum likelihood estimate, we simultaneously optimize the size and the location of these ambiguity sets. And third, and for me, most surprisingly, we realized that these ambiguity sets that we're constructing need not be confidence interval at all. So let me show you a simple example. So say we want to guarantee a lower bound on the true return with 90% confidence. So on the left-hand side, you see the standard concentration and quality set using Hafting bounds. Now you can take the same idea and construct a Bayesian confidence interval or a Bayesian credible set. That's the middle picture. But it turns out that these sets are also too pessimistic and not unnecessarily large. So we propose a new method for constructing optimized sets, which are much, much smaller, but still give you the 90% confidence guarantee. And you see an example on the right-hand side. You see the set is much, much smaller, and it's by no means 90% confidence interval in the Bayesian sense. If you'd like to know how this works, please come to see our poster. So let's look at some simple examples of the performance of this method. So on the x-axis, you see the number of samples. On the y-axis, you see the calculated error of the return. So the bigger the error, the more conservative the method is. So the topmost, the worst performance is the concentration inequality. This is the Hafting bound. You see that introducing the Bayesian assumptions makes it a little better, but our method RSVF, which is in red color, significantly outperforms the standard Bayesian confidence interval. The blue line is simply using the mean model, which gives you no confidence guarantees at all. So these are results with an uninformative prior. If we look at an informative hierarchical prior in a small MDP, we can see even more dramatic improvement compared to the Hafting bound. So our Hafting bound in this case is practically useless, but our Bayesian and optimized Bayesian confidence intervals are much better. So to conclude, we proposed a new data-driven method for constructing robust ambiguity sets. The main ideas is we use Bayesian models to capture prior knowledge. We optimize not only the size, but also the location of these ambiguity sets. And we realized that the ambiguity sets need not be confidence intervals. The advantages of this method is that it's robust, but not too robust. It still gives you finite sample guarantees. And in many ways, you get priors that are easy to define. One disadvantage is that this method increases the computation complexity quite significantly. Thank you.
Thank you. Questions? We have time for a quick question. All right. In that case, let's thank the speaker again.